Hello and welcome to our first practical application of machine learning. Before I start, I'm going to tell you that now the training wheels are officially off. I'm not going to be holding your hand when it comes to very simple stuff when dealing with R in RStudio and just writing code, okay? So having said that, let's just go ahead and start this right away. So we're going to build a linear regression model, okay? The first thing we do is just right off the bat, this comes from experience. I've built a lot of models and I've worked with a lot of data. So I know that intuitively, you can just anticipate that you're going to need some libraries. So you can just go ahead and load those now or later when you come across a situation where you need one of these libraries, that you can load it then. But I prefer to load whatever I might need before I start working. So I'm loading these three libraries and we got to run this, load that into the environment. And for the data set that we're going to be modeling, I'm just going to steal a data set from another library that we're not going to be discussing, but it's called Model R. So just go ahead and just install Model R very quickly. There is a particular data set within this library that we're going to be using, and that's why we're installing it. But we're not going to be using this library for anything. Don't worry about it. So Model R. The data set is called sim1. So simulation 1. We'll just save it into sim1. And if you want to see, or I guess we can just put it here, this is what sim1 looks like. We can view sim1. It's a simulated data set. It's designed just to make it easy. It's very small, just, for beginners. Like, it's used as an example on how to build models and for machine learning, that kind of stuff, before working with real data. So it is a simulated data set. It is a fake data set, but it's going to help us understand what building models and fitting models means and how it's done. Okay, so let's go ahead and plot this data set. So as you can see, we have an X and a Y. So we can just go ahead and use ggplot2. We use the sim1 data set and the aesthetics are X and a Y. And we'll just go ahead and do a scatter plot. Okay. So there we go. This is the data set we have. Assume it's random. When you plot data set, so in the next section, we're going to go into what we call exploratory data analysis. And this is something you should do before you decide on which models to use and that kind of stuff. It allows you to get a sense of the data. So here we plotted the data. So this is a very rudimentary exploratory data analysis. We plotted the data and we can see that it has, in general, there is a linear correlation. It's like, it's not a quadratic data set. It's not something that's crazy going all over the place. There is some sort of correlation between X and Y such that, as X increases, Y does increase. So when you plot your data, you might find relationships like this that'll help you better decide on what model to use, right? So having done that, having seen the data, let's now create our family of models. So we can tell here that this is a linear data set, right? It has a linear relationship. And we said that the linear lines are described by a slope and by a y-intercept. So ggplot2 actually lets you draw lines, right? Linear lines. So there's a geom function called, so let's start ggplot2. Let's just put in our data and plot this first of all. Okay. Geom point. So we plotted the data. There's a geom called AB line, and this lets you define in aesthetics an intercept. So let's go ahead and define here, like the intercept is, let's just make a random line. So let's define the intercept to be 20, okay? And you can define a slope. And let's say the slope is like -2, okay? -2. And if we were to plot this, we would see a line. So remember layering. So we layered this plot on top of this plot. So we have our original data set, and now we have a random line, that has a 20 y-intercept. It's not reaching 20 here because this is not exactly at 0 here. So, this probably stops at around like 0.2 or something, and that's why it's not here. So imagine this continues going forward, but it has a slope of -2. So this is just some random line. And this line is described by two parameters, the intercept and the slope, okay? So with that in mind, if we wanted to generate a family of linear lines, a batch of linear lines, just a bunch of random lines, because we don't know what line would most accurately describe this data set. So we want to generate, maybe 100 or 200 or 500 different lines, random lines with different intercepts, different slopes, and then decide on which one is more accurate, more close to our data set. So that would mean that we would need to generate, like let's say we want to generate 100 different lines, we would need to generate 100 different intercepts and 100 different slopes and plot them all. So let's do that. Let's create a variable called models. And these will describe our family of models, the many models that we're going to be generating. And so we have to define a parameter A. Let's call this the intercept. Let's refer to it as parameter A, right? So just A1. And let's generate. So there are many functions in R for generating random numbers. I think we discussed this in previous videos, but to use the uniform distribution, those not familiar with statistics, it doesn't matter, but those that are, to use the uniform distribution to generate random numbers, we use a function called runif. Stands for random uniform. And you can define, let's say we want 10 random numbers, and we want the range of these numbers to be between like 0 and 1. So you get 10 numbers, random numbers that are located or situated between 0 and 1. So you can change the range, and you can change the numbers you want to generate. So let's say we want to generate 250, okay, different lines, random lines. So random uniform, runif, 250, we need to generate 250 intercepts or A1 parameters. And let's say the range, so we can see from here that, the intercept should be maximum, let's say like from -20 to 40, okay? The possible range for the y-intercept, -20 to 40. So if you want to just run this on its own, go ahead and do that, Control Enter, and there we go. This is 200 randomly generated intercepts, okay? Now let's do the same thing, and this time for parameter 2, which is the slope. And again, we need 250 of them. And let's say that, let's go up here. So the slope would be something, so slope is rise over run, right? So let's say -5 to 5, right? That's a good range. So let's generate slopes between -5 and 5, and let's generate 250 of them. So we can see that here we have 250 slopes ranging from -5 to 5. So if we were to generate this, so let's go ahead and, so we created our models. So these are our models, right? These describe our models, because we already proved that for this particular type of model that we're creating, this family of models, the linear line, we need two parameters to describe it. So these two numbers precisely describe that line that we had seen. So any set of these two numbers would precisely describe another specific line. So now we're describing 250 random lines, right? 250 random lines. So these are random intercepts and random slopes, completely randomly generated. So having done that, let's now plot the model. We've generated our models. You can see in our environment, we have our models, and you can pull it up here, right? And here, right, we have our original data set, okay? And here we're plotting a line, but now instead of plotting a single line, let's plot all our lines. So let's change the data so you can actually provide different data within one ggplot definition. So here we have our actual data, sim1, representing the data. So geom_point, the scatterplot, uses that data. And then here we're going to define a new data set. So we're going to define it to be our new models. So now geom_AB_align will start using this data set for its plotting. And now we want to, remember in models we have A1 and A2. So we put A1 here and A2 here. And let's say that, because there are going to be a lot of lines, we want to make them somewhat transparent so they're easier to see. So let's set the alpha or the transparency to 25%. And then let's just go ahead and run this. And there we go. We have our original data set in the background. and we have a set of 250 randomly generated lines. So these lines are actually models, right? This is the family of models that I was referring to in the previous video. We have a family of 250 models. Now, if you notice, these models, for example, are very inaccurate, right? They're a very bad summary of these points. But, as the lines get more and more, their slopes end up becoming like this, they become more accurate of a description of the data set. But if the slope is like this, but the line is located up here, right, because the intercept is too high, then it's too far from the data set. It doesn't properly describe the data set. So we want to find the parameters A1 and A2 of the model among these 250 models that best describes this data set. And that will be our fitted model, okay? So here we're generated family of models. Here we did some, exploratory data analysis. And in fact, we can just pull this up here because, this also counts, I guess, as exploratory data analysis. So we did that and we generated a family of models. Now, let's create some functions to help us with the next step. So let's create a function called model1, okay? And what this function does is it takes in a set of parameters, okay? And we call the parameters A. So this will be a vector of two parameters, A1 and A2, okay? And it takes in the data that we have. And based on the data, it's going to give you a prediction. And this prediction might be completely off, right? So this will make more sense when I complete writing the function. So remember, a linear function or a linear line is described by this function. So let me explain what's going on here. So this is a function, right? And let me actually give you an example of using this function so it makes more sense. So this is just something, we're creating to make it easier for us to define or to find the fitted model. So now what's happening here is our simulated data, right? Our actual data set consists of two rows of data. So this is the input and this is the output. We want to come up with a model that we can supply an input, an X to, and that we get an accurate Y output to. So that's the whole point of what we're doing. We want a model that can describe the relationship between X and Y. When you input X, you want to have a number Y that's close to what it would actually be, okay? So this means that we need to have a function that we can experiment with in which we can plug in, we can supply a model to and plug in the X's and see what the model would output as a Y. So then we can compare that output of the Y with the actual Y. So here, this is a model, right? This is what we're supplying is a description of one of these lines, just a random line, that has a slope 7 here, right? This will go into A, and then A, the first element of A is here. It will have a slope of 7, and it will have, it will have a slope of 1.5, and it will have a y-intercept of 7, okay? So, and it will use the input from our data set to generate output. So this is its estimated output. For this model, right, the predicted outputs are these. So what we want to do is we want to compare these outputs with the actual Y column in our training data set. And that's how we can assess the accuracy of any model. In this case, the model is 7 and 1.5, okay? So now remember, to assess closeness of a model and the actual data set, we said that there is a common method used called root mean squared deviation. So root mean squared deviation. And let's create a function to help us do this. It's called measure distance, right? Because we want to measure the distance between the Y output of our model and the Y of the actual data set. And we'll do that using this function that we're creating. So this is very good for you to get used to creating your own helper functions, right? We want to input a model into this function and actual data. And then we want this function to use the model to predict a set of y values like we did here and compare it with the actual y values in the data. So the difference for each of these predicted y values and each of the y values in summation 1 can be found using data y, which is the y column in the actual data set, minus model 1 model data. So this here is the same thing as this, right? We just replaced this model with mod here, so we can supply it whatever we want. So this will give you this result, predicted y values, and these are the actual y values. So the difference between them will give you a vector of values that measure or calculate each of the two y's. And then we square root the mean of the difference squared. That's what we mean by root mean squared deviation. So we calculated the deviation, we're squaring it, right? And then we're calculating the mean of it, and then we're calculating the square root of it. So this will give you one single value, and that should be not an accurate description, but should give you some sort of description as to the accuracy or the error or the closeness of your model's predicted y values and the actual y values you're trying to predict. So, for example, right, let's measure the distance of this model here. Let's measure the distance of this model, right? And we find that, this is a value, okay? Right now, this might not mean anything to us. What is 2.6 or 2.7, right? But now when we put in another model, right? Let's put in some random other model, let's say 6 and 1. And we see that this model is way worse. It's far more distant than the previous one. So this is a less accurate model, and the one we previously had was more accurate. Because look, it's like twice as good.